Today we're going to focus almost entirely on acid-base titrations. Titrations we're already familiar with as a laboratory procedure. It's where we use the molarity of a known reactant and the stoichiometry of a reaction to determine something about another reactant. Maybe its concentration or the number of grams that are present in an unknown, something like that. In acid-base titrations, we're titrating, of course, an acid versus a base. So the reaction that's going on is an acid-base neutralization. It's interesting to study these things because they give us some idea of the dynamics of acid-base reactions, how these reactions change over time, and we'll develop an idea of distinct zones where the reaction mixture follows different rules and pH can be determined by different methods depending on what's there in the reaction vessel. We'll start out with some quizkins. First of all, carbonic acid, H2CO3, and the bicarbonate ion, HCO3 are making a buffer that controls pH at 7.40. Your body naturally sets up this buffer. The Ka of carbonic acid is 4.4 times 10 to the minus 7th, and we want to know how does the concentration of the bicarbonate ion compare to that of carbonic acid in your blood. Well, since this is a buffer system, the Henderson-Hasselbalch equation is probably going to be useful. pH is pKa plus the base 10 logarithm of the conjugate base, which in this case is the bicarbonate ion, over the acid, which is H2CO3. And we can use number of moles here, or we can use concentration. Let's use concentration. So solving this equation, what we really want to do here is find the ratio of concentration of base to acid. And so we're going to solve for that. So pH minus pKa is equal to base 10 logarithm of HCO3 concentration over H2CO3 concentration. Now it said that the Ka for carbonic acid was 4.4 times 10 to the negative 7th, so that means the pKa is just the opposite of the base 10 logarithm of 4.4 times 10 to the minus 7th, and that turns out to be 6.36. So plugging that into this equation, that's telling us that 7.40, the pH of the blood, minus 6.36, our pKa value, is equal to the base 10 logarithm of the ratio that we're trying to find, carbonic acid concentration under bicarbonate ion concentration. So if we take 10 to both sides, we can get rid of the log here. So 10 to the 7.40 minus 6.36 is the ratio of bicarbonate ion concentration to carbonic acid concentration, and that's what we're trying to find. So take 7.4 minus 6.36, raise 10 to that power, and you come up with 11.0. So what this is telling us is in your blood, the concentration of bicarbonate ions is 11 times higher than that of carbonic acid. This next question says if your blood pH drops below 7.4, you get acidosis, a condition called acidosis. If your blood rises above 7.4 by much, you get a disorder that's called alkalosis. So based on the equilibrium below, which is the one that produces the carbonic acid, and based on our answer to the last question, which disorder is caused by holding your breath? Well, the pH of your blood is going to be equal to the pKa of carbonic acid plus the base 10 logarithm of this ratio of bicarbonate ion concentration to carbonic acid concentration. What would happen if you held your breath? Well, there's going to be no change to pKa if you hold your breath. That's a constant. That's a characteristic of carbonic acid. But if you look at this equilibrium here, holding your breath would cause your bloodstream CO2 concentration to rise. And if concentration of a reactant rises, then by Le Chatelier's principle, we're going to see a shift in this reaction to the right. When the reaction shifts to the right, that's going to produce more H2CO3. So if you look at this ratio, that will change. An increase in carbonic acid concentration is going to make this ratio a smaller number. The logarithm of that ratio will then also be a smaller number, and so you're adding a smaller and smaller number to pKa, which means the pH, which is the result of adding those two numbers together, is dropping. So acidosis is the condition that's caused by holding your breath. Well, now let's get into some titrations. Just to review what a titration is, you measure out one solution using a burette. In our first example here, there's going to be a strong base in the burette. And then you put the other reactant below the burette and react the two according to a known equation. And then you can tell what's going on mole and volume-wise by just knowing the molarities and how the reaction occurs. So we're going to do this by example, and we're going to look at three possibilities. The first one is a strong acid versus strong base titration. So in this one, we've got in the flask down here a strong acid, and then we're adding to it from the burette a strong base. So up until we reach the equivalence point where the reaction has completed, the limiting reactant is going to be the strong base. What's the neutralization equation? Well, anytime you have a strong acid reacting with a strong base, the anion from the acid and the cation from the base are always going to be spectators, and you end up with this equation. H plus plus OH minus makes water. And this is a reversible reaction, but it's not very reversible because the K for this reaction is going to be 1 over Kw, and Kw is 10 to the minus 14th, so this is going to be a very forward reaction. In fact, we can consider it a one-way reaction. All acid-base titrations can be separated into different phases, and so let's take a look at several of these different phases. The first phase is going to be before the titration even begins. Before any base has been added, what you have is just a strong acid solution. And if you have a strong acid solution, you're going to determine the pH by just what's the concentration of the acid and how many protons are released per mole of the acid. We're going to work with a monoprotic acid here and use this as an example. 25 milliliters of 0.1 molar HCl are present, and we want to know what's the pH. Well, the pH is going to be equal to, of course, the minus the base 10 logarithm of H plus concentration. We'll use that concept throughout. HCl is a strong acid, so that means it's going to split up completely to give you H pluses and Cl minuses. So if I had a 0.100 molar concentration of HCl to start with, that means my concentration of H plus is 0.100. So pH is the base 10 logarithm of 0.100, and that is equal to 1. The next phase of the titration is before we've reached the equivalence point, so in other words, it's not neutralized yet, but some base has been added. What you have here in this phase is just a less concentrated strong acid. And it's less concentrated for two reasons. One is some of your acid has reacted, and so there are fewer moles of acid in the solution. But the other thing that's happening is you're adding stuff from the burette, so the volume is increasing. And since molarity is going to be number of moles of acid divided by the total volume, both of these changes are going to result in a decrease in concentration. So here's an example. Let's say you had 12.50 milliliters of our strong base, which we're going to have in our example here as 0.1 molar NaOH, same molarity as the acid, that are added to the starting quantity of 25 milliliters of 0.1 molar HCl. So let's figure out what's present here at equilibrium. First of all, here's our neutralization equation. H plus plus OH minus is making H2O. Initially, we had in the flask 25 milliliters of a 0.1 molar HCl solution. So let's figure out how many moles are there. We'll take our volume, 25 milliliters, and we're going to multiply this by the molar concentration, which was 0.100 moles of HCl, and therefore 0.100 moles of H plus per liter. If you multiply these two together, you find out that there are 2.50 millimoles of H plus initially present. So we'll put this in our chart. 2.50 millimoles. Now, what have we added? Well, we've added 12.50 milliliters of a solution that is also 0.100 molar, but this is 0.100 molar OH minus concentration. So we'll multiply these together and we find that we have added 1.25 millimoles of OH minus by adding 12.5 milliliters of NaOH. So 1.25 millimoles of this have been added, and we haven't created any water by this reaction yet. So what's our change? Well, in the past we have created these Rice charts using variables like x to represent the stoichiometry, but we actually don't have to use x here because we know what's going to happen. OH minus concentration is going to drop to nothing. It's the limiting reactant here. So we're going to lose all 1.25 moles of OH minus. That means we will lose 1.25 moles of H plus because of the one-to-one stoichiometry, and we'll gain 1.25 millimoles of water. At equilibrium, or I should say end, at the end of this change really, here's what's left. We don't have any OH minus left. We will have created 1.25 moles of water, but we don't really care about that. However, we will have dropped our H plus concentration by 1.25. So if you take 2.5 and subtract 1.25, you end up with 1.25. So the concentration of H plus now is equal to 1.25 millimoles divided by the total volume. Well, the volume before we began the titration was 25 milliliters, and then we added to it 12.5 milliliters. So we can find our H plus concentration by doing this division problem, and it's 0.0333 moles per liter. Take the base 10 logarithm of that and take its opposite, and you find your pH, and it's equal to 1.48. So our pH is rising, but it's not rising much. When we started the titration, we had a pH of 1. Now we have a pH of 1.48, and we're halfway through the titration. We're halfway to the equivalence point. Because these concentrations are the same, both are 0.1 molar, it should take an equal volume of NaOH to neutralize 25 milliliters of HCl. So we're halfway to the end point at this point. At the equivalence point, what's present at the equivalence point is you don't have any more H plus because you've neutralized it all, and you haven't added any additional OH minus yet, and so what you have is a neutral solution. It only contains the cation from a strong base and the anion from a strong acid, and those are both contributing to a neutral solution. So your pH will be 7 at the equivalence point. After the equivalence point, you no longer have any H plus because it's all been reacted. And now you have added additional OH minus. So you have a strong base solution. You can determine the pH in a strong base solution by finding the OH minus concentration by taking the remaining moles of OH minus, the part that didn't get neutralized, and subtracting by the total volume. So now our example problem is saying we have now added a total of 62.50 milliliters of 0.1 molar NaOH to our original 25 milliliters of 0.1 molar HCl solution. Let's figure out what the pH will be after this addition of base. So once again, our neutralization reaction is H plus plus OH minus, irreversibly producing water. Now, we started out, we already figured this out earlier, with 2.50 millimoles of H plus before the titration began. At this point, we've added 62.50 milliliters of our base solution, which is 0.100 moles of OH minus per liter. So that means we have added, in total, at this point, 6.25 millimoles of OH minus. So I'll put that here, 6.25 millimoles, and then water we really don't care about. Here's our change. After the equivalence point, H plus is now the limiting reactant because we have less H plus than we have OH minus. So that means we're going to use up 2.50 millimoles of H plus. That means also we will react 2.50 millimoles of OH minus. And we will gain 2.50 millimoles of water, but we don't really care. At the end then, when this is done, we won't have any H plus. We already know that because we've gone beyond the equivalence point. 6.25 minus 2.5 is 3.75. So that means we have 3.75 millimoles of OH minus that haven't reacted with any H plus, and so that's an excess reactant here. Water, we don't care. So the concentration of OH minus in this reaction is 3.75 millimoles divided by the total volume. Well, we've added 62.50 milliliters to the original 25.00 milliliters, and so that's our total volume. This concentration works out to 0.0429, and if you take the base 10 logarithm of that and find its opposite, you'll have POH, and the POH here is 1.37, and then if you subtract 14 minus 1.37, you'll have the pH, and so the pH is equal to 12.63 at this point beyond the equivalence point in the strong acid, strong base titration. Next, we're going to look at a weak acid, strong base titration. So the burette still has a strong base in it, but now we have a weak acid in the flask below the burette. The neutralization reaction looks like this. Now we have our weak acid, we're going to call it HB, and it's reacting with OH minus from the burette. That will produce water, H2O, because the H from the acid is going to be donated to the OH minus and it's going to make water, and B minus, which is the conjugate base of our acid. Now this reaction is going to be the reverse of a weak base ionization reaction. If you just imagine this thing flipped around so the products are reactants and reactants are products, you've got a weak base ionization reaction. And that's going to have a very low Ka value. And so this reaction can be treated as a reaction that goes virtually all the way to completion when we add additional OH minus. So it's a one-way reaction, just like we saw before. So titration reactions are always going to be one-way reactions. Let's look at the different phases of this titration. Before any base has been added, what we have is a weak acid solution. And you could set up a rice chart if you wanted to, but the end result always ends up being the same thing. We've seen this over and over again. The H plus concentration is just going to be equal to the square root of Ka times whatever the original concentration of the acid was. So if our weak acid solution is a 0.100 molar acetic acid solution, we can find our H plus concentration if we know what Ka for acetic acid is. H plus concentration is going to be equal to the square root of, for acetic acid, it happens to be 1.8 times 10 to the minus fifth, and if you're ever in doubt about these things, you can look them up. They're easy to find on the internet, times our concentration of HB, which is 0.100 molar. Work this out, and you find out that the H plus concentration is 0.00134, and if you take the base 10 logarithm of that, its opposite is pH, and that is 2.87. So compared with our strong acid, strong base titration, we are starting out at a higher pH. It makes sense because it's a weak acid, it's not a strong acid. After we've added base, but before we reach the equivalence point, something interesting happens. If you look at the neutralization reaction again, it's HB reacting with OH minus, and it's going to produce water and B minus. Now if I start out with a certain amount of HB, and I add a bunch of OH minus, that OH minus is all going to react. Before the equivalence point, the stuff that comes out of the burette is the limiting reactant. So I'm going to end up with no OH minus, and I will subtract some number of moles, I don't know what, I'll maybe say X, however many moles of OH minus I added, and I'll end up with something less than the initial concentration of HB. But there still is going to be some HB there. I'll call the concentration HB final. I'm going to add some water. I'm going to add some moles of B minus, and there weren't any originally. Now I have a concentration of B minus. I'll call that B minus final. So what's here? I have my acid still, but I also have the conjugate base present in a water solution. Well, that's a buffer. So I can find the pH of a buffer system by using the Henderson-Hasselbalch equation. Let's take a look at this example here. So we have our 25 milliliters of acetic acid from the original problem here. And now we've added 12.5 milliliters of our strong base, which is still 0.1 molar NaOH like in the last example problem. Let's figure out what the pH of this buffer is. So looking at our neutralization reaction, which is HB plus OH minus producing water plus B minus. Translating that to our reaction here, it's HC2, H3O2, that's our weak acid, plus OH minus from the burette is making water plus, now our B minus is C2H3O2 1 minus. We originally put 25 milliliters of a 0.1 molar acetic acid solution in here. And from the last example titration, we should know that that's 2.50 millimoles that we started with. Now, how much OH minus have we added? 12.5 milliliters of a 0.1 molar solution. And from the last example, you might remember that that is 1.25 millimoles. Water, we don't really care. There isn't any acetate ion before the neutralization takes place. So what's the change? Well, my limiting reactant is OH minus, so I'm going to lose 1.25 millimoles, all of the OH minus. I'm going to also lose 1.25 millimoles of acetic acid. I will gain 1.25 millimoles of water and of acetate ion. So at the end of this change, I will have 1.25 millimoles of acetic acid left, no OH minus, water, I don't really care, and acetate ion, I will now have 1.25 millimoles. So according to the Henderson-Hasselbalch equation, the pH is equal to pKa plus the base 10 logarithm of base concentration, or base number of moles in this case, 1.25, over acid concentration, or acid number of moles, which is 1.25 in this case. So when you're at this particular point in the titration, that goes to 0 because it's the log of 1. So the pH, when you're halfway to the equivalence point, is equal to the pKa. Now, if we hadn't gone halfway to the equivalence point, this ratio wouldn't be 1, and you could still figure out pH. It just wouldn't be as simple. So the pKa, what is pKa? Well, if you take the negative of the base 10 logarithm of 1.8 times 10 to the minus fifth, because that's Ka for this acid, you would get 4.74. So that means our pH at this point in the titration is 4.74. So it's gone up, and it should be holding pretty steady. We're not going to do it, but if you added another milliliter and then another milliliter and then another milliliter, you would see that the pH was rising only very slowly, because buffers do that. Buffers resist changes in pH. Now let's look at the equivalence point. You might be tempted to just say, well, it's neutralized, so the pH is 7. But in fact, that wouldn't be true. Let's look again at our neutralization reaction. HB is our generic acid. It's reacting with OH minus, and it's producing water and B minus, the conjugate base. Now, at the equivalence point, we don't have any of this left anymore. We've reacted it all by adding enough OH minus, just enough OH minus, to use it all up. But in the meantime, we've been creating some amount of B minus, and that's still there, and it'll always be there now. So we have a solution that contains a base. So we really have a weak base solution. How are you going to find the pH of a weak base solution? Well, we know that the OH minus concentration in a weak base solution is always going to end up being the square root of Kb times the original concentration of the weak base, or in this case, the equilibrium concentration of the weak base. So we can figure that out. So here's our example problem. We have now added 25 milliliters of 0.1 molar NaOH, which is just enough to neutralize 25 milliliters of 0.1 molar acetic acid. What is the pH here? Going back to our original neutralization equation again and setting up another rice chart, I have acetic acid reacting with OH minus, producing water and acetate ion, C2H3O2 1 minus. My initial number of moles of acetic acid were 2.50 millimoles. I have now added 2.50 millimoles of OH minus too. Water, I don't care. This didn't have any before the neutralization. Now, what's the change? I have used up all 2.50 millimoles of acetic acid and all 2.50 millimoles of OH minus, because it's a one-to-one stoichiometry. I'll gain some moles of water, but I don't really care. But I have also gained 2.50 millimoles of acetate ion. So at the end of this, I don't have either of these left anymore at all. Water, I still don't care. And this is 2.50 millimoles of my conjugate base. So how do I find the pH? Well, the concentration of OH minus, remember, is going to be equal to the square root of Kb times the initial concentration, or the equilibrium concentration, of B minus. So we need to find two things. One is what's Kb, and the second one is what is this equilibrium concentration of B minus. Well, let's work on the Kb part first. The Kb for a weak base is equal to Kw divided by the Ka for its conjugate acid. So Kw is 1 times 10 to the minus 14th. The Ka for acetic acid was 1.8 times 10 to the minus 5th. So that means our Kb here is 5.6 times 10 to the minus 10th. Now let's work on the concentration of acetate ion. The concentration of our weak base, C2H3021-, is going to be equal to the number of moles that are present in the solution, that's 2.50 millimoles, divided by the total volume. But the volume is the 25 milliliters that we started with, plus the 25 milliliters that we added, so a total of 50 milliliters. Our concentration is now 0.0500 molar. So plugging that into this equation, we find that the OH minus concentration is 5.6 times 10 to the minus 10th times 0.0500, and we take the square root. And this gives us OH minus concentration equal to 5.3 times 10 to the minus 6th. So if we take the log of that and change it to a positive, we end up with a POH, and that POH value is 5.28. And if we subtract 5.28 from 14, we have pH, and the pH is 8.72. So the pH has risen, and in fact it is higher than pH 7 when we're at the equivalence point. After the equivalence point, what do you have? Well, going back to our neutralization equation for our generic HB acid, reacting with OH minus, producing water, and producing B minus, we have now added so much OH minus that the HB is all gone. We've produced a bunch of B minus, and that will always be there. But now we're starting to add OH minus that can't react with anything because the other reactant is gone. So the concentration of OH minus goes up and up and up and up. Since OH minus is a very strong base, that's going to overpower this effect of this weak base, and all we have left really is a strong base solution. And we'll find pH by looking at the concentration of OH minus. Concentration of OH minus is just going to be the number of moles of OH minus that haven't been reacted in the neutralization reaction, so in other words the extra stuff, divided by the total volume. So in our example problem, beyond the equivalence point, we now have added 62.50 milliliters of our 0.10 molar NaOH to the original 25 milliliters of acid. What's going to be the pH here? Well, we had acetic acid reacting with hydroxide ion, producing water, and acetate. Initially, we had 2.50 millimoles of acetic acid. We have now added 62.5 milliliters of OH minus, and its concentration was 0.1 moles per liter, so that means we've added 6.25 millimoles of OH minus. No acetate before the change takes place, don't care about water. So the change is, well, the limiting reactant is now going to be our acetic acid. So we have lost 2.50 millimoles of acetic acid, which means we have also lost 2.50 millimoles of OH minus. We add that same amount to both products. So when we finally reach our end here, we don't have any of this. We have 3.75 millimoles of OH minus remaining, and we have 2.50 millimoles of acetate ion. Don't care about water. This isn't going to produce a significant amount of OH minus because it's a very weak base compared with straight OH minus. So that number of millimoles is what's going to dictate our OH minus concentration here. So what is our OH minus concentration? Well, we have 3.75 millimoles in 62.50 milliliters plus the original 25 milliliters that were there before the beginning of the titration. This gives us a concentration of 0.0429, which means our pOH, if we take the base 10 logarithm of that number and change the sign, is 1.37. And then if you subtract 1.37 from 14, you get the pH, and the pH is 12.63. Now, you might recognize that number as the same exact pH when we had added this amount to the strong acid in the strong acid, strong base titration. So the behavior of this titration, of this mixture of reactants, becomes identical once you reach the equivalence point. Let's look in detail at one more type of acid-base titration, and that is a weak acid versus strong base titration. So now we have a strong acid, like HCl, for example, in the burette, and we're adding it to a weak base. What's the neutralization reaction? Well, we're starting with a weak base, which we're going to call B-, and from the burette, we're adding to it H+, and that's going to produce the conjugate acid of this weak base, HB. Let's look at the phases of titration. Before we've added any acid to the solution, we just have a weak base solution. And pH is going to be dictated by the concentration of OH-, which is just going to be equal to the square root of Kb times the initial concentration of our weak base. So let's use this example as we build our titration curve here. 25 milliliters of 0.1 molar NaOH. So we're sticking with the same starting volume and the same concentration as we've had in the last examples, and that makes the math simple. Well, NH3 has a Kb that's equal to 1.8 times 10 to the minus fifth. You may recognize that. That's exactly the same number as the Ka for the acetic acid. So what is our OH- concentration? Well, OH- concentration is equal to the square root of that Kb, 1.8, times 10 to the minus fifth, times the initial concentration of our weak base, which was 0.100 moles per liter. If we take the square root of that product, we find 0.0013 is the OH- concentration. So that means our pOH is equal to 2.87 if you take the base 10 log of that and change the sign, and subtract 14 minus 2.87 and you get the pH, and the pH is 11.13. So that's our starting point. Now, we're adding acid, so our pH should drop. Next phase of our titration is after we've added some acid, but before we reach the equivalence point. Now, just like we saw before with weak acid versus strong base, we have a buffer system. And here's why. I started out with B-, I added to it H+, and I created HB. If I'm before my equivalence point, I add some H+, and it uses up some B-, but leaves us with some final concentration of B-, but there isn't any H+. However, I have created some HB, exactly the same number of moles of H+ that I've added, and that gives me a final HB concentration. So I've got an acid and its conjugate base, both present in the same solution, and that makes it a buffer. So here we are at 12.50 milliliters of 0.1 molar HCl added to our ammonia, our 25 milliliters of 0.1 molar ammonia. What's the pH? These calculations might look pretty familiar to you because they're going to be a mirror image of what we saw before. So our neutralization reaction here is NH3 plus H+, creating NH4+. And we had 25 milliliters of 0.1 molar NH3 to start with, so initially that means we had 2.50 millimoles of NH3. We have now added 12.5 milliliters of 0.1 molar H+, so that means we have 1.25 millimoles of H+, and then no neutralization has taken place at first. What's the change? Well, we're going to lose the number of millimoles of H+ that we added, because that's the limiting reactant, so minus 1.25. We also are going to lose minus 1.25 here at NH3, and we're going to gain 1.25 millimoles of NH4. So when this change is done taking place, we'll end up with 1.25 millimoles of ammonia, no H+, and 1.25 millimoles of NH4. So according to the Henderson-Hasselbalch equation, for this buffer, pH is pKa plus the base 10 logarithm of concentration of weak base, so that's NH3, divided by weak acid, which is the NH41+. Let's figure out what pKa is for NH4+. So we know this relationship, pKa for an acid plus a pKb for a base has to add up to 14.00. So let's find out what pKb is by taking the opposite of the base 10 logarithm of 1.8 times 10 to the minus fifth, which is the Kb for ammonia. This gives us 4.74. So 14 minus 4.74 is our pKa for ammonium, and then ends up being 9.26. So pH is equal to 9.26 plus the base 10 logarithm of, well, now we know we have 1.25 millimoles of both of these, base and acid, and so this goes to 1 again, and so the log of 1 is 0, and so our pH is just 9.26. So our pH is dropping. And once again, we've got a buffer system, so if we added another milliliter, then another milliliter, then another milliliter, we wouldn't see the pH change by much because buffers maintain a steady pH to a certain extent. The next phase in our titration is at the equivalence point. So looking at our original weak base, we've added H plus to it and created some HB. We started out with some B minus, but we're at the equivalence point. We don't have any of it left because we've exactly reacted with H plus. That means we haven't added any extra H plus either, so we have neither of these in solution. What we do have, however, is some HB, and that's a weak acid. So the weak acid is going to dictate the pH. Concentration of H plus in a weak acid is just equal to the square root of the Ka for that acid times the concentration of the acid. So we want to take the equilibrium concentration of HB and multiply it by Ka, take the square root of it, and we'll get H plus, and then we can get pH from there. So in our example, we're now at the equivalence point, which means we've added 25 milliliters of our 0.1 molar acid solution. Let's figure out what the pH would be. So it's NH3 reacting with H plus to produce NH4 plus. Originally, we started out with 2.50 millimoles of NH3. We've now added 25 milliliters of H plus at 0.1 molar concentration, so that's 2.50 millimoles of H plus. At the beginning, we had no ammonium. So that's initial. The change, we're going to lose 2.50 millimoles of both reactants, and we're going to gain 2.50 millimoles of product. So at the end, at the equivalence point here, we have none of the weak base or the H plus, but we have 2.50 millimoles of NH4 plus. So what's the concentration? Well, the concentration of our NH4 plus at equilibrium here is going to be equal to 2.50 millimoles divided by the total volume. We added 25 milliliters to 25 milliliters, and so we now have 50 milliliters. Concentration here is 0.050 molar. So the concentration of H plus is going to be given by the square root of that times the Ka for NH4 plus. So what's Ka? Well, we figured out the pKa in the last problem is 9.26, so we'll take 10 to the minus 9.26, and that will give us the Ka value, and it ends up being 5.6 times 10 to the minus 10th. So our concentration of H plus here in this solution at the equivalence point is equal to the square root of 5.6 times 10 to the minus 10th times our 0.050 molar concentration of NH4 plus. And when we work this out, we get 5.3 times 10 to the negative 6th. If you take the minus base 10 logarithm of that, you get pH, and pH is 5.28. So at the equivalence point, we are in fact below 7, which we'd expect to have because we have a weak acid solution. After the equivalence point, what do we have? Well, remember we started out with B minus, we reacted with H plus, and we produced HB. So we don't have any of this anymore. We do have some HB, but now we've added a whole bunch of more H+. And just like we saw with the strong base weak acid solution, the H+, because it's so much stronger of an acid than the HB, is going to dominate this solution, and we're not going to be concerned about the amount of H+ that's produced by the weak acid. It won't be enough to even bother with compared with this straight H+ we're dumping in here from the burette. So, our example problem, we're now at 62.5 milliliters of 0.1 molar HCl that's added to our original 25 milliliters, and we want to know what is the pH. So we started out originally with 2.5 millimoles of NH3. We have now added 6.25 millimoles of H+, and before the titration began, we had no ammonium. We have now lost 2.50 millimoles of NH3, and that's all the H+ we can lose because NH3 is the limiting reactant after we reach equivalence point. So that means by stoichiometry we have gained 2.50 millimoles of ammonia. So when we reach the end of this change here, we don't have any ammonia. We have 3.75 millimoles of H+ that are not neutralized, and we have 2.50 millimoles of NH4+. This is not a strong contributor to acidity, so we're just looking at the H+ here that's remaining in solution. So the concentration of H+ is going to be equal to the number of moles of H+, 3.75 millimoles, divided by the total volume. So we started out with our 25 milliliters, and then we added to that 62.5 milliliters. So the concentration of H+ that we have here is 0.043 molar. If you take the opposite of the base 10 logarithm of that, you get pH, and pH turns out to be 1.36. So the pH has dropped pretty precipitously after the equivalence point because we just have a strong acid solution and it continues to grow with more addition of H+. A strong base, strong acid, we're not going to go through this whole thing, but it follows the same logic of strong acid versus strong base. You start out with a strong base. Until you reach the equivalence point, you still have a strong base, but it's becoming more and more dilute, so it's weaker. At the equivalence point, your pH will be 7, and then after the equivalence point, you'll just have a strong acid. We understand acid-base titrations graphically by using something called the titration curve, and I'm going to draw a simple titration curve here. On the x-axis of a titration curve, we have the volume of OH minus added, and this is for acid versus base titration. So the acid is in the flask, the base is in the burette. So on the x-axis, we're plotting how far along are you in the titration, how much hydroxide ion have you added. And on the y-axis is pH. And just for reference here, here's pH 7, which is neutral. In a strong acid versus strong base titration, here's how things look. We start out with a low pH, and we keep tracking along with a fairly low pH, but it's getting higher and higher gradually. It's almost linear through this phase. Then, very suddenly, this becomes almost straight vertical until you reach the equivalence point. So the equivalence point is right here. And then shortly after the equivalence point, it starts to go like this. So you're above pH 7 after the equivalence point, and you have a concentration of strong base that's increasing, so the pH is rising, and again you reach this almost linear zone here. The pH at the equivalence point for a strong acid, strong base titration is 7. Now I'm going to draw on here what a weak acid versus strong base titration would look like and how is it different. First of all, we start out with a higher pH, so the initial pH is higher. It jumps rapidly, but then a buffer gets formed. And then you have this nearly linear change again for a while until the buffer capacity is exceeded. So in this initial zone, it's just a weak acid, and then you have a buffer that gets quickly established, and then the buffer's capacity gets exceeded and the pH starts to rise until you reach the equivalence point. So the equivalence point for this weak acid strong base titration is going to be higher. It's going to be above pH 7. Then after that, the curves are identical. So because you just have a strong base solution that continues to rise with additional OH minus. Now there's one more feature that we can put on this weak acid, strong base titration. And that is, if this is the equivalence volume here, halfway to the equivalence volume, your pH will be equal to pKa. For a base versus acid titration, so the base is in the flask now and the acid's in the burette, so we're adding H+, so on the x-axis we're plotting volume of H+, and on the y-axis we're plotting pH. Let's first do strong base versus strong acid. So strong base is in the flask, strong acid's in the burette. We start out with a high pH. As we add more and more acid, we neutralize some of the base, and we still have a strong base, but it's less and less strong all the time. Very quickly, we reach this almost vertical portion until we reach the end point, the equivalence point, which will be at 7. And then after that, we have a strong acid solution that gets stronger and stronger and stronger as we add more and more acid. How is a weak base versus strong acid different? Well, for one thing, the weak base is going to start out with a lower pH. After quickly establishing a buffer, it will go along like this until the buffer's capacity is reached, and then we'll start to see a drop in pH until we reach the equivalence point, and we'll reach this equivalence point at some pH that's below 7, because a weak acid will be present there. After the equivalence point, the shape of the strong acid, strong base, and weak base strong acid titration curve will be the same shape. Well, this has been a pretty long video. There's been a lot of calculations there. It's a lot of information. I suspect that if you're like me, you're probably going to have to go back and review this a few times. The only way to really get a good grasp on this is to work problems. So make sure that you're doing your practice problems on titrations. And on the AP exam, you're going to find out that straight titrations that are labeled as titrations are pretty rare. Instead, what you're going to find is problems that aren't called titrations, but you can recognize that they're basically the same thing as a titration and use the different phases of titration to figure out, is it a buffer, is it a weak acid, is it a strong base, what is it, at what different part of the titration, and then just match that to the problem that you're actually given.